Just want to start off by saying I also have nothing against Russians. Just going to getting that out there. So welcome everybody. As you heard from the introduction, I'm David Savage from MikroTik SA, and I'll be giving a talk about the various dynamic routing protocols that you might deploy in your network, whether or not they are a good idea, when it's appropriate to use them, and a little bit about what they are going to do. Just a quick outline. Cover who I am, what the presentation is about, what you're going to learn, and then I'll move through the dynamic routing protocols. Hopefully not too technical, so I think everybody will be able to keep up with it. And then also think about when you should be using these protocols. So which protocol is appropriate in which situation, and how best to deploy it into your network. And then best practices, perhaps you could look in some instances at combining various protocols together, and what you need to support larger networks. So looking at moving into MPLS and possible related services with that. Just very quickly, a little bit about MikroTik SA. First of all, we're an independent company. We're not owned by or affiliated to MikroTik Latvia in any way. We are, of course, official support and training partners for MikroTik. And really what we do is we specialize in all forms of wired and wireless networking. So we offer things like business independent point-to-point links, support services, backbone services, SLAs, ad hoc consultation, that sort of thing. For myself, I'm a MikroTik certified consultant and trainer. I've been a trainer for about 11 years, been working with MikroTik for 13, 14 years, somewhere around there. I teach people how to use MikroTik. I teach them how to best implement MikroTik in their network, and then I also try to help them to run their network on an ongoing basis. Okay, more on a ad hoc rather than dedicated support services. And just say more recently, I've also started partnering with Terraco, and we are now starting to do Terraco Tech Days. That's also based around deploying MikroTik in data center environments and pairing with other providers, and so on. So what is this all about? Well, MikroTik offers a number of dynamic routing protocols that you might choose to deploy into your network. And it could be confusing as to which protocol is suitable for which environment and for which network setup. And you might just go, well, I've always worked with BGP, so I'm going to stick with BGP because that's what I know how to use, and that's going to be it. Or I've only ever used RIP or OSPF, something like that, and perhaps not try to look at some alternatives that might be more efficient for your setup. So in terms of fundamentals, just going to look at the 4 RIP, OSPF, MME, and BGP. So first of all, RIP is the Routing Information Protocol. It is what we call a distance vector protocol. So I'll come back to that in a minute and explain what that is about. It was available in 3 versions. You got version 1, version 2, and then RIP-NG, essentially RIP next generation. A quick table to illustrate the differences between them. We can probably ignore RIP version 1, as I think it's very much a deprecated protocol, not used anymore. But RIP v2, even that, don't find it very often, but it is occasionally seen in networks. If we're really looking at RIP v2 versus RIP NG, the primary difference there is RIP NG supports IPv6. Okay. Otherwise, they operate in mostly the same way. They both use multicast. RIP v2 supports authentication. RIP NG doesn't, and I'll explain why that is now. And they are both classless protocols, which RIP v2 also supports classful. Classful means that there is no prefix associated with an update. So you can't use it in a CIDR or classless interdomain type of network. So RIP v1, RFC is listed there. The routes are specified by IP destination network and hop count. Key there is the routing table was broadcast to all stations on the attached network. So RIP v1 was known for rather heavy network utilization in terms of the number of updates it sent and the number of broadcasts that were being sent through the network. Also doesn't support classless interdomain routing, therefore only the destination is sent, not the subnet prefix. And as I said, deprecated really since we started using RIP v2. So RIP v2, main thing there is, first of all, it defined the subnet mask and also defined the gateway. The other difference is the routing table is sent to a multicast address as opposed to a broadcast address with v1. So that did, to some extent, reduce network traffic. Okay? However, still had the problem of the entire routing table being sent out in every single update. It also featured some sort of authentication, so you could enable authentication so that presumably you could not have random RIP devices trying to join into your network. RIP next generation, essentially an extension of v2, but this was designed for IPv6 networks. In this case, again, the routing table is sent to a multicast address. In this way, once again, we are trying to reduce network traffic. And while RIP v2 did support authentication, RIP NG did not. And the reason for that was an initial requirement of IPv6 was that it was meant to use IPsec at all times for authentication. Anyone who's actually used IPv6 knows that it's not really the case. You can decide to or not. It's more of a recommended than a must-use. In terms of how RIP works then, RIP is a dynamic routing protocol, and as I said, it's a distance vector protocol. So what it does is it looks at the number of hops between source and destination, and it counts only the number of hops to determine the best path through the network. Okay. It is compatible with things like ECMP, which is equal cost multipath routing. What I mean by that is if there are multiple hops to the same destination and there are the same number of hops in both cases, then it can use both of those connections simultaneously. Okay. So it has a few decent features there in terms of it can find the shortest way to get to a destination, and it can build up that routing table dynamically. Okay. But it is rather limited in that it can only count number of hops. So you can't have any other factors brought into it. Things like individual link cost or multiple areas or hierarchical structures. It has none of those types of features. The other major limitation, which we'll get to in a second, is the hop count, which is the number of routers or hops that RIP is allowed to traverse. Hop count then is essentially how many hops or how many routers do we have to transit in order to get to our destination. As mentioned, the path with the lowest hop count will be the preferred path. That's how it's going to decide to get to the other side. And in order to prevent routing loops, in other words, a packet bouncing from one device to another or getting halfway down the network and deciding that the best path was back on the return path, okay, RIP limited the maximum number of hops to 16. Okay. So that means it actually says the maximum hop count is 15, but that's because the sort of TTL of the packet would be 16, so it could transit through 15 devices. After that, it would be considered as being in a route loop of some sort, and it would drop. This, of course, means that RIP would be constrained to fairly small networks. You couldn't use it in a very large enterprise-wide environment where there were going to be many hops planned between your source and your destination. RIP network updates are exchanged between routers periodically. The updates are always broadcast, or rather multicast on the network. The full routing table is sent in updates. Okay, this could be a problem, especially if you have a very large routing table. It means those update packets could be quite large in size. The other issue is routers always trust on the information that they receive from neighbors. Okay, in RIP this was known as routing on rumors. Okay, it just assumed if the packet came from a neighbor that the information was completely accurate. Okay, no sort of versioning information or anything like that, as we would have in OSPF, to confirm that the information received is actually the latest version of information and accurate in some way. The other issue with that is convergence or calculation of the best path is also slow, okay, just in terms of how the protocol operates. OSPF is the open shortest path first protocol. Okay. OSPF uses a link state routing protocol or link state routing algorithm as opposed to RIP, which is a distance vector algorithm. Currently, we have OSPF in two versions. There's OSPF v2 and v3. v3 is, again, meant for IPv6. It differs somewhat from v2 in terms of it only uses interfaces and not networks, and there are a few other minor differences, but fundamentally it operates in the same way. OSPF can use a number of different methods in order to initiate and maintain a peering connection to another device. So we have modes like broadcast, multicast, point-to-point, point-to-multipoint, and all of those can be used to control how neighbor relationships are built and how quickly routing tables are updated and so on. OSPF also defines in broadcast nodes, if you have a large number of routers on a single node, it can define the use of a designated router, which can be used as a centralized point for updates. Again, since all routers are not sending full routing tables to each other, they are all communicating with a central device. This allows us to cut down on the amount of traffic used in order to push out those routing updates. So I said OSPF is a link state routing protocol. It works by building up a map of the network and then running an algorithm known as the Dijkstra shortest path algorithm against that information in order to determine what is the best path to any other network host. So OSPF was developed as an IGP, which is an interior gateway protocol. What I mean by that, it was designed to be used inside networks. So not really as an inter-network or inter-AS routing protocol, more designed to be used in your organization. It's a network layer protocol. It works on protocol number 89 and has an administrative distance of 110. Again, not to get too technical, but what that indicates is when it gets inserted into the router's routing table, the distance that it appears as is going to be 110. It's a fixed distance. It's not alterable by you, so we term that the administrative distance of the protocol. OSPF, as I said, uses multicast. That's address 224005, which is defined as all SPF routers, and that's how communication will work. They'll all join that multicast group, and they'll use that to communicate with each other. In terms of how link state routing works, the idea behind it is that every node communicates with each other, with other nodes, and what they'll indicate is what links they have, links really being interfaces. Interfaces can be any kind of physical, Ethernet, wireless, virtual interface, Ethernet over IP tunnel, anything of that sort. And they all communicate with each other using link state announcements in order to get the same set of information. Once all of the routers have the same set of information, they run the shortest path algorithm against that Dijkstra algorithm that I mentioned. And in that way, they'll build up a map of the best path through the network and the fastest path to any given destination. The main difference there between OSPF and RIP is with RIP, it only looks at hop count. However, with OSPF, you can modify the values of each and every link along the way, and in that way, you can, as an administrator, determine how a packet moves through the network. So by assigning higher or lower costs to links, you can in some way influence how path decisions are going to be made through the network. Taking it a bit more advanced, you can install other protocols on top of OSPF, such as, for example, traffic engineering, which can take additional types of constraints into account. There we're talking about things like taking a different path when a certain path is under load, or applying some kind of bandwidth limitation on a per link basis to influence exactly how that traffic is going to move through the network. Another advantage that we can leverage in OSPF is through the use of a system called BFD. If I just illustrate the problem, and this is a very common problem you will have, especially when using third-party fiber connections, third-party layer 2 links, third-party VLANs, and so on. If you can just see my diagram over there, we have router A and router B. In between them is, let's call it a third-party CPE, or it could be your own device. It might be a set of MikroTik devices. Maybe it's a, I don't know, 60 gigahertz LHG link or something along those lines. Okay. The problem with something like that is you have a transparent layer 2 link. Okay. However, between router A and the CPE, the only thing that it can check is the status of that Ethernet interface. Okay. If the wireless link itself goes down in between, the router is not going to know about that. It doesn't know that the link has gone down. The physical Ethernet interface is still running and still active. Okay. What's going to happen in a case like that? Well, it does depend on the protocol. And again, might not be a wireless link, could be a VLAN provided by any third-party provider. Okay. Could be any other kind of physical link in between those two locations. So in the case of protocols like BGP and OSPF, they work by continually trying to monitor the state of the connection or the device on the other side. So what they'll do is, in the case of OSPF, it will send something called a hello packet, and that hello packet is used to determine if that device on the other side is still alive. By default, it'll send that every 10 seconds, and after 4 hello packets are not received, it will then reach something called the dead interval, okay, which is when it will then decide that that remote site is down. So that means from the time that my layer 2 link drops until the time that it actually figures out, we're looking at around 40 seconds. Okay. That means in that time, it's still going to try to route down that link, and it's still going to try to actively send packets through that connection. With BGP, it can be even worse. BGP's standard hold time is 180 seconds, so there you're looking at up to 3 minutes until it decides that the remote site is actually down and tries to take action on it. However, there's a very cool little feature in MikroTik, and it's also supported by other systems, and that is called BFD, or bidirectional forwarding detection. Okay. What bidirectional forwarding detection does is it gives an independent monitoring of the link state. And it's far, far more sensitive than the 40 or 180 seconds defined by OSPF and BGP. In fact, you can define that yourself. The default settings on BFD will give you a failure report in approximately 1 second. Okay. However, if it's something like a wireless link where it might not be as reliable, you might adjust that time up and say, well, do it after 2.5 seconds or 5 seconds or something along those lines. Or you could even make it more sensitive and say within 0.5 of a second, I want to be notified of this link down, or whatever time period you like. You can define that in the BFD settings. Essentially what that does is BFD signals to the upper layer protocol that the interim link is down, okay? And then the upper layer protocol will react as if that interface was physically down. So it'll be as if the Ethernet interface had been unplugged, and it will instantly mark that neighbor as dead. Okay. So instead of waiting 40 seconds, or sometimes even longer, you could have just a couple of seconds until OSPF knows that that device is down and removes those entries from the routing table, okay, thereby forcing it to find an alternative path out of that particular device. In order for BFD to work, you enable it on both sides of the link. And in the default settings, it really is just a matter, you can see on my, sorry, I know the slide's not too clear, but on my OSPF here, it's just a matter of a checkbox that says use BFD. The same applies for BGP. Again, click the checkbox, use BFD, make sure that is operational on the other side as well, and BFD will start running. Okay, you can observe that on the router. If you look in the routing BFD menu, you can see things like neighbors, and then also set various parameters for how sensitive it is and so on. Another great feature that OSPF can give us is its support for TE, or traffic engineering. So OSPF TE is an extension of OSPF. Okay? The TE, or traffic engineering information, can be carried along in OSPF LSAs, which are link state announcements. Okay? It's carried inside something called an opaque LSA. So an opaque LSA is one that can carry information for other protocols. To some extent, this makes OSPF what we would term an extensible protocol. In other words, it's not just able to carry information for itself, but also for other types of systems. So we can build an MPLS network on top of OSPF. We can use OSPF as our MPLS network carrier. And then on top of MPLS, we can enable traffic engineering for our particular OSPF area. And then we can manipulate the network in all kinds of cool ways. Yeah, we can place bandwidth constraints on links. We can enforce almost like a queuing system on links, where it only allows a link to reach 80 or 90% of its capacity before switching over to an alternative path. We can steer traffic through our network in any way that we want to. So we can define separate paths for maybe data, video, voice, and so on, along with backup paths, and steer traffic along those lines in any way that we want to. So we are now bypassing the shortest path algorithm, or in some way combining shortest path with traffic steering to define exactly how we want traffic to move through our system. So in the RSVP, Resource Reservation Protocol, essentially OSPF is used to flood the network with information about available links and available bandwidth reservations, and in this way decide how best to get traffic through the network. Also giving us the ability to utilize normally unused links, because you might not feel they have enough bandwidth, but with being able to set those constraints, you can still use the link safely and be assured when a certain bandwidth is reached, it tries to switch over to something else. The next thing is BGP. BGP stands for the Border Gateway Protocol. As I said, OSPF is a link state protocol. BGP is a path vector protocol. Not like RIP. RIP is a distance vector protocol based on hop count. BGP is a path vector based on the number of networks it has to traverse. I'll get back to that now. Broadly speaking, BGP comes in two forms. We have exterior BGP, normally just called eBGP. That's used for fundamentally routing across the internet, for joining networks together. And then we have interior or iBGP, which mainly is used for sharing routing information between eBGP devices or eBGP peers. BGP natively supports IPv4 and 6, so there are not different versions of BGP. There is only one version, which is BGP version 4. And BGP is also the only protocol that can handle networks the size of the internet. Mainly what BGP is used for is to exchange path information between networks that are connected to the internet. So BGP relies on something called an ASN, an autonomous system number. An ASN is a number assigned to you by IANA, it's the Internet Assigned Numbers Authority. Attached to your AS number is your block of public IP addresses, which you'll presumably have gotten from Afrinic or some other regional internet registry. And together, your block of IPs plus your ASN defines your presence on the internet. So BGP is the protocol that is used to tell other providers about things like what your AS number is and what your IP network range is. So that's how you advertise your presence to the rest of the world. The only requirement is each AS, autonomous system, must have at least one router that can talk BGP and connect to another peer. Although, of course, it would be common for you to have multiple BGP routers on your network talking with external peers, because, of course, nobody would want to rely on a single device to route all of their traffic to the internet. So BGP's main function is it exchanges NLRI, network layer reachability information. In other words, saying, I am this AS number, these are my IP ranges, and this is how many networks you will have to move through in order to get to me. So aside from building peering relationships with other networks and transporting information between those networks, we have two types of peering relationships. If you are peering BGP between two devices within your own network, so it will be within the same AS number, then we call that iBGP or interior BGP. If the peering relationship is between two different AS numbers, then we would term that eBGP or exterior BGP. And really the main function of iBGP, interior BGP, is to carry routing information between exterior BGP devices. It's so that the devices on the borders of your network know which other networks they are attached to, and they know the appropriate path to follow when they want to move traffic between the different networks. Just an illustration there, you can see in each AS, we have our routers connected together with iBGP, and then between ASs, the red lines, those are eBGP peering connections, sharing information between different autonomous systems. BGP then is designed as a method to route between networks. So BGP only cares about the shortest path between different networks. It doesn't care about the internal structure of any network. It doesn't care that inside the network you might have 10 hops or you might have a single hop to get from the one side of the network to the other. It only sees, or it sees the entire network as one hop in the path. So BGP uses something called AS path length. In other words, how many ASs or networks do I have to traverse to get to my destination? And that's one of the methods that it uses to decide which is the shortest path to a given destination, just by how many networks it needs to move through. Because BGP doesn't care about internal network structures, that is one of the reasons why it can handle networks the size of the internet. Okay, so it only cares really about the big picture, not about the little details. Having said that, though, iBGP's main function is to send information between these exterior connected peers. Okay. However, it is possible to allow iBGP to distribute things like your internal or your connected and static routes inside your network, and in that way operate as an interior protocol. Okay. It is capable of doing that. However, there might be a few disadvantages to doing that as compared to using something that was designed to be used as an IGP, such as OSPF. First of all, when you configure BGP, it's very much a manual process. You need to configure each and every peer individually. Whereas with OSPF, peers can be discovered dynamically, the relationship between peers can come up automatically, and they can establish a network environment very, very quickly. BGP also has a very complex path selection process. So BGP doesn't just look at how many hops there is to a destination or what is the shortest path with the lowest cost. It has many, many more decision-making algorithms when it does something called its best path selection. I'll cover that briefly on the next slide. Also, if you run iBGP, you need a full mesh between every single router on the network. So iBGP can't run like OSPF where you have small bundles of routers that are connected to each other. Every single router has to know about every other router all the time. This can create very, very complex network setups if you have a large number of routers. Either you would need to have, as I said, a full mesh, which could lead to a very large number of peers. Alternatively, you could use something like a route reflector, which is used as a central point for creating the peers, but it's still a manual process of creating every single link to the route reflector, and you presumably need multiple route reflectors, primary and a backup at the very least, and it is quite an administrative overhead to maintain all of those. The other part is compared to something like OSPF, the convergence is relatively slow. So how quickly it's going to build up the routing table can take some time. It is a bit of a ridiculous example, but for example, you could have two eBGP routers converging two full routing tables on the internet. It could take something like 25 to 30 minutes, depending on the devices that are being used. In any event, it's not going to do it in a matter of a few seconds like OSPF might. The other issue is it won't have any detection of link state when configured between loopback devices, which is the recommended setup. So normally you don't configure iBGP on a physical interface or physical IP. You would move that to a loopback, which is not attached to any physical interface. Although, of course, having said that, once again, you could use something like BFD for detection of peer downstate, and that might help mitigate that in some way. I don't want to go through this in detail because it's quite a complicated process, but just to give an idea of the BGP best path selection process. So you can see there we have 11 possible steps that we can go through, and these are defined by different BGP parameters that you would set up in route filters, and this is what you would use to influence best path selection through the network. Whereas with OSPF, if you want to influence best path, you change the value or the cost of a link, and that's really it. There. Tell it this link is more expensive or that link is cheaper, and that's all you have to do. Whereas with BGP, might be quite a while defining your best path selection and attributes. There. And if you don't do this, then you might have some very unpredictable results. You might find BGP is resorting to something like which is the highest IP address on which interface in order to decide a path out the network. Okay. As it gets further down that list, it starts getting more and more desperate in terms of how it decides as to how it's going to get out the network. Another protocol which you might never ever have heard of is MME, which is the Mesh Made Easy protocol. Yeah. So MME is a MikroTik routing protocol, and it's suitable for IP-level routing in wireless mesh networks. So it's based on ideas from a protocol called Batman, which is the better approach to mesh networking. And the idea behind MME is it's designed to be used in wireless networks where the links might be unstable. Okay? The links might go up and down, the signal strengths might change, the speed of the links might change, you might get more or less packet drops through a connection over time. Okay? And it's designed in an environment like that where network conditions are highly variable. Okay? It's designed to be able to change the best path selection based on something that is not link cost, okay? Or is not path cost, but based on things like, for example, which link has dropped the most packets in the last couple of minutes or something along those lines. So routing information is contained in a message that consists of the IP of the originator and an optional list of prefixes. And if a node receives a message, it will just rebroadcast that message to other devices. So unlike OLSR, which is another type of mesh protocol, okay, MME doesn't look at network topology information. Okay, so it doesn't really care how the network is constructed, and it doesn't construct routing tables in any way. Okay? Instead, the way it works is it creates a set of IP tunnels between every single node on the MME system. It then keeps track of packets that are received and sequence numbers, and in that way it can tell how many packets are being lost. Okay. So it then starts basing its routing decisions on which path currently has the least number of lost packets, okay, and which is going to be the most efficient or least latency method of getting through that network. So the main idea behind MME are some observations we can make about wireless or specifically mobile mesh networks. And that is, first of all, it can be impossible to know the exact topology of the network. As you have devices moving around, connecting to different access points or meshing together in different ways, your network topology is changing all the time. If the topology changes, okay, and it triggers routing table recalculations, then the CPU overhead can be significant. So running something like OSPF in a rapidly changing environment could trigger a huge amount of network updates and so on. So in order to avoid that, MME only cares about the best single next stop neighbor to a particular destination, and it avoids routing table calculations. Okay, so it tries to do away with all of that. Otherwise, the other thing it does is it can carry information about gateways to the internet, okay, which is the best path out of the network, and dynamically can set up default routes. So that really covers a bit of theory about each of the protocols that I want to talk about. Next thing I can look at is what are the practical applications of these protocols. First thing I'll start with is with RIP. I don't know that much of an argument can be made to still use RIP in your network. We have the 15-op limitation combined with the constant resending of the full routing table, slow convergence, not very scalable, limited to small networks. It doesn't sound like a great thing. However, having said that, it is very easy to set up. Really a few clicks of some interface menus and you're ready to go. So, I guess if you're feeling particularly lazy and wanted to do a very, very quick dynamic routing protocol setup, you might consider RIP in a small network. Okay, and said, yeah, maybe we should call it the Rest in Peace Protocol. In fact, yeah, how long are we talking about? My many plus years, I've only come across one network using RIP ever. Yeah, so I guess that says something. As far as MME, or Mesh Made Easy, and I took this straight from the MikroTik wiki, which fundamentally says that MME is not meant to be a replacement for dynamic routing protocols. Its function is to try to find the most efficient path through a network with highly dynamic changing link content. So in something like a mobile mesh network, I can picture a situation where you have a number of trucks or vehicles fitted with mobile APs, and they're constantly moving around and constantly having to connect to each other. That might be an argument for where you would use MME. Yeah. What you're saying there is it's just going to take too long for something like OSPF or RIP or anything else to update. Yeah. So by using the Mesh Made Easy protocol, we're only caring about which was the best path as of a few seconds ago, and let's get the packet out of this network as quickly as we can. So recommended in networks where conditions are changing. You have latency increase and decrease all the time, link flaps, disconnects, reconnects, and so on. Roaming mesh devices, those are your ideal types of situations. Okay, so OSPF, first of all, it's a very widely deployed routing protocol. It can converge a network in a few seconds. So once it knows the information about other devices, it can put together a map of the network really, really quickly. Rapid topology updates based on the status of links, which are really interfaces. It has many features allowing imposition of many different types of policies to control how routes are going to be propagated through the network. Okay, and that's appropriate to keep traffic local for load balancing, load sharing, selective routes importing, assigning different costs to links, controlling exactly how traffic moves in and out of your network. It offers a hierarchical structure, so you don't have to run it in a single domain. Yeah, you can have multiple OSPF areas, and you can do clever things like aggregate network ranges behind those areas. So you can keep your routing table really small by allowing some kind of area aggregation inside your network. Okay. And I mean, I don't have to tell you, the smaller your routing table, the more efficient your network's going to be. I mean, that would just be good sense. It also has different network types. So we've got broadcast NBMA, which is non-broadcast multiple access, point-to-point mode, point-to-multipoint mode. And those are meant for different ways for hosts to establish links to each other. So by choosing the optimal method to join your hosts together, okay, you can get the best performance out of OSPF. Okay. I'll just plug at this point, if you want to learn all about this, come on the Routing Engineer course. Okay, we cover this kind of thing extensively. And as we mentioned, it's compatible with BFD, which also allows us to rapidly detect when a link has gone down and take appropriate action on that. Why do we want OSPF then? Well, it's a very well-established interior gateway protocol. It's easily deployed in an existing routed network. It's an open standard, so compatible with a very, very wide range of vendors. Supports IPv4 and IPv6. Rapid convergence, great performance. It can also be used along with iBGP to carry iBGP messages between eBGP routers. Okay. Since iBGP is working between our loopback addresses, iBGP needs some way to know about the other devices. So iBGP can use something called a recursive lookup through an OSPF network to find the most efficient path to a device on the other side, or an eBGP speaker on the other side of the network. And it allows for building additional services on top, such as MPLS, VPLS, which are pseudo-wires or layer 2 networks between your clients, traffic engineering, and all of that can be rapidly deployed on top of an existing OSPF network. If it's already in place, it's not too much of a big additional setup to get MPLS operational. Or are we going to go with BGP? So it's easy. If you want to connect to other networks on the internet, you must use BGP. There's no real choice there. So it makes that choice really, really easy. However, using it as an interior protocol, it does use very complex decision-making algorithms to determine the best path in and out of the network, which is great for eBGP because it allows you to set very good network policies in how traffic should leave to other destinations and return. So great in terms of the internet, but might make it overly complex in terms of your interior network. As I said, it can be used as an IGP. It does require additional configuration. It's going to be a lot more complex than OSPF to set up, but certainly I've seen people use iBGP successfully inside their network and be quite happy with the way it performs. So perhaps in your particular environment, it would be an appropriate choice. Again, depends on how much time you're willing to set up or to put in to get the best configuration. It's also compatible with BFD. As I said, that gives us rapid detection of link downs and allows the device to determine independent of interface state when another device is not available. You can also, if you have an existing OSPF and MPLS network, you can deploy iBGP on top of that in order to use some kind of signaling, okay? And that can be used in layer 3 VPN environments. So that is if you are using virtual routing and forwarding and you need to carry that VRF information across your enterprise. So BGP signaled VRFs can carry information around your entire network, and the same applies for BGP signaled VPLS. So that allows you to rapidly deploy VPLS tunnels through your network almost on an automated type of basis. Other options you might look at, I've seen this deployed. Perhaps you can combine OSPF and BGP together. So the idea behind there is you might use OSPF as your core network protocol, carrying information between your internal routers, okay, and then use BGP to carry client ranges across your OSPF network. The idea behind that is because you are isolating the protocols from each other, all your client ranges are carried inside BGP, all your core ranges carried inside OSPF, so you don't have to mix the networks together. You will never see client ranges on your core network, and again, your clients will never see your core ranges on their external networks. So, you know, could be quite a good setup in a number of situations. Okay. The only issue I'd have with that is, you know, just remember if you set it up, somebody else in future might need to administer this. So make sure everybody else knows exactly what you're doing if you try to go through a situation like that. Okay. In conclusion then, what I'd like to say is there is no one best protocol that's going to do everything. Okay. The closest might be BGP, where you could say, yeah, I could use it inside and outside my network, but you're probably talking about a fair bit of administrative overhead in doing that. Okay. Each protocol will have its advantages and disadvantages. So hopefully I've given you some insight to indicate when you should be using which protocol and where in your network you should be deploying that. Okay, if there are any questions or comments, it'll be fixed in RouterOS version 7, so that's there. But we do have a couple of minutes, so if anyone wants to throw some questions out, I'm happy to take them now. Okay. Nothing. Either was very comprehensive or I confused you thoroughly, so one of the two. Okay. Otherwise, as with the others, the slides will be published. All my contact information is there, and feel free to try to get hold of me at any time with any additional questions. Thank you.